So today, let us talk about some special graphs. So suppose that we have a graph that has n vertices. So let's say n vertices. So in this case here, n is equal to 5. So for a graph to exist, it does not mean that it has to contain an edge. So this could be a graph. This is a graph that contains 5 isolated vertices. Is that okay? So they are very lonely. So this could be a special graph. This is an empty graph. It does not contain any edge. Oh, in contrast, if there is an edge between any pair of vertices, so in our example here, this will be the graph, then we call this a complete graph because all the edges are complete. They are there. So this is a complete graph. And usually, we denote a complete graph by using the symbol big K, and then using the number of vertices written here as the subscript. So this is called a K5, a complete graph with 5 vertices. So we can have K1. So what is K1? K1 is just a graph that has a single vertex. What is K2? So K2 is a graph that contains 2 vertices, and there is an edge joining every pair of vertices. So it is K2. Is that okay? So how does K3 look like? K3 looks like this one. There are 3 vertices, and then there is an edge joining every pair of them. And K4, how does K4 look like? So K4 looks like this. So there are 4 vertices, and there is an edge joining each pair of vertices. So this is a K4. Is that okay? So we have a K5 there. So complete graph also has a name, another name. People call it a clique. So clique is actually an English word. It means that a group of people, usually very small, they have common interests, and then, it is. So for outsiders, it is difficult to join into this group, but for the insiders, they are very friendly to each other. So, okay, or in Chinese, maybe we can translate this to 小圈子. So this is a clique. So sometimes it is a clique of 1 vertex, a clique of 2 vertices, a clique of 5 vertices. And why do we use the K to represent it? Because it is pronounced as complete graph. So K sounds like right? Okay, okay. And then, okay, so we have also a different kinds of graphs. We call it a cycle graph. So cycle graph is the case where the vertices, they form a cycle. So this is the case. This is a cycle graph with 3 vertices. This is a cycle of 3 vertices, or simply, this is a cycle with 4 vertices. This is a cycle with 5 vertices. Is that okay? So a cycle graph has a property that if you start at any vertex, and each time you move to a new vertex, then you can always go back to itself in n steps. Is that okay? Because it is a cycle. And cycle graph, we use the symbol C to represent it, because C is the first letter of cycle. So it is called a C3, this is called a C4, and this is called a C5. Okay. And then, if there is cycle graph, we can further extend it to something called a wheel graph. So what is a wheel? So what is a wheel? A wheel, what is a wheel? Very good. So a wheel, the wheel on the bus go round and round. So it looks like this. Okay, so it has something like this. So this looks like a wheel, am I correct? So a wheel graph is a cycle graph with an addition vertex that is placed at the center. So this is a C3. If I add a vertex at the center, then I join this to every other vertex, then this is a wheel graph. So we call it W3. 3 for the outer side, and then there's always exactly 1 in the middle. So we can have a 4 wheel. So this is a 4 wheel. So it is like this. Is that okay? And then we can also have a 5 wheel. So we start with a cycle, and then we place something at the center, we join them to each other. Okay, so this is a wheel 4. This is a wheel 5. So we use W to represent it because it is the first letter of this wheel. Okay? Yeah, simple things, yes. And then we can also have a graph called a cube graph, or n cube, n-dimensional cube. So you will see why we call it a cube soon, or n cube. So it is defined like this. So first of all, I call a simple edge that has 2 vertices Q1. Is that okay? This is called a one-dimensional cube. So we use Q, it is because Q is like cube, okay? And then to get Q2, we duplicate Q1. So we have 1 copy of Q1, we have another copy of Q1, so there are 2 copies of Q1. Am I correct? And then you can have 1-1 correspondences between the vertices here. Okay? And then we join the corresponding edge together. So this is called a Q2. Is that okay? How about Q3? So Q3 is we have 2 copies of Q2. So this is 1 copy of Q2. And let's say we have another copy of Q2. Is that okay? And then we join the corresponding vertices together. So we join this to this one, we join this to this one, we join this to this one, and we join this to this one. Is that okay? So this is a Q3. Is that okay? And then for Q4, you have a Q3 here. Q4 is formed by having a Q3 here, and then another Q3 here, and you join the corresponding vertices together. So this is Q4. So why is it called a cube? If you look like this, this is a cube. This looks like this shape, right? Is that okay? So this is a Q2, this is another Q2, and you're joining the vertices together. Okay? Now, cube is very useful. Okay? So imagine each of these vertices is a computer in a very large network. Okay? Okay? So before that, perhaps let me give you some extra information about how a cube could be represented. Okay. So first of all, we may represent each vertex here by some bit string. So let me call this bit 0 and this bit 1. Is that okay? And then for this one, originally there are 2 copies of Q1. So all of them are called 0 and 1. But then this is the first copy, so I call it 0, 0 and 0, 1. And this is the second copy, so I call it 1, 0 and 1, 1. Is that okay? Is that okay? And for this one, originally there are copies of Q2, 2 copies of Q2. So let me call it 0, 0, 0, 1. And then this is 1, 0, and then this is 1, 1. So this one is also 0, 0, 0, 1, 1, 0, 1, 1. Is that okay? Now, because this is the first copy, so I add a first bit 0 to represent it. So this is 0, 0, 0, 0, 0, 1. This is 0, 1, 0. This is 0, 1, 1. Is that okay? And for this one, it is 1, 1, 1, 0, 1. 1, 0, 0, 1, 0, 1, 1, 1, 1, and 1, 1, 0. Is that okay? Now, after adding the bit string, what is so special about this graph? So first of all, I have 2 questions for you. So if it is Q4, how many vertices are there in this Q4? How many? How many are there? So Q1 has 2 vertices, right? Q2 has 4 vertices. Q3 has 8, and Q4 has 16. Very good. So the number of vertices, so the size, the number of vertices in a Qk or Qn is 2 to the power n. Okay? And then what? And then how do we define a Q4? So one way is you draw 2 Q3 and join them together. But the other way is you list out all the possible strings of length 4. Each one corresponds to a vertex. So let us look at the simple thing here. So for Q2, to draw Q2, one possible way is we find out all the possible strings of length 2. So it is 0, 0, 0, 1, 1, 0, and 1, 1. Am I correct? And then we are joining 2 vertices together if the string differs by exactly 1 bit. You look at it, 0, 0, and 1, 0. You change this bit, you get 1, 0. Is that okay? 1, 0, and 1, 1. Is that okay? You're changing only 1 bit, and then you get this one. Is that okay? And then 0, 1, and 1, 0, it is just differed by exactly 1 bit. So this is some interesting result. So if you look at Q3, then what will happen? So you have all 8 vertices. Each one is with a different string. This one is 0, 0, 0, 0, 0, 1. All the possible length 3-bit string. We can define the 8 vertices. And 2 vertices are joined to each other. So these 2 are joined because they are differed by exactly 1 bit. These 2 are joined to each other because this is 0, 0, 1, this is 1, 0, 1. They are differed by exactly 1 bit. If you are okay with this, could you please raise your hand? Okay. Now, with this idea, so we can think of this as, so if you have Q10, then what will happen? Q10, you will have a node, you will have a very large graph with 1024 vertices. Am I correct? With 1024 vertices. And then, if you imagine each vertex represents a computer, and then each edge represents a link that I can send information from one computer to another computer directly, then we will be interested in what is the longest distance inside this graph. So if I am a computer, I want to send a message to my friend at another computer. How far away could that friend be? Okay, if you look at it, Q2, the farthest distance is from this node to this node, you have 2 edges. Is that okay? And for Q3, the farthest distance may be from this node to this node. Am I correct? Am I correct? And then there are going to be 1, 2, 3 edges. And for Q10, the farthest distance is going to be 10 edges. Reason. If you look at it, each one corresponds to a bit string, right? So bit string cha cha xxxxx. So a 10-bit string. So let's say this is my computer. And let's say this one is my friend's computer. Let's call it 000000000. Is that okay? Okay, so each one of us can be represented by a 10-bit string. Okay, and what is how to transmit a message? For instance, I can check. So to transmit the message, I can try to change my bit string into something that looks like my friend's bit string. If it is not the same, I change from one bit to another. Okay, so let me just give you an example. Let's don't use Q10. Q10 is too large. Let's use Q5. Okay, so assume that we're at Q5, and let's say my node corresponds to the string 10110, and my friend's string is corresponding to 01011. Okay, then what I should do? Okay, so I compare the first bit of my string and my friend's string, and they are different. So I try to change the first bit into my friend's one. But I know that there is just one bit difference between this one and this one, so I can send a message from this one to this one directly. Is that okay? Because okay, now the second bit is different. So what I should let me copy this down. 01011. So the second bit is also different. So what I should do, I changed my second bit. Is that okay? And then what is next? The third bit is different. So I changed my third bit. Is that okay? The fourth bit are the same, so I do nothing. And then the 5 bit are different, so I change my 5 bit. So I can send a message from my computer. This is my computer. Let me call it X. To my friend's computer. Let me call it Y. Simply by looking at the strings that we are using. I'm using this string 10110, and my friend is using 01011. Okay? And then what I know that I can change it bit by bit so that eventually, at the end, my bit string can become the same as my friend's bit string. If I change only one bit each time, then there is a direct link from this computer to this computer. A direct link from this computer to this computer. Is that okay? And the maximum number of bits that we need to change must be 5 in this case, because there are just 5 bits. Okay? So in Q5, the maximum number of edges we need to use is 5. And in Q10, the maximum number of edges we need to use is 10. Is that okay? So in that sense, this n cube, you can have a network that contains many, many nodes. But then the distance is very, very short. Even if I have 1,000 nodes, then the distance is only 10. If I have 1 million nodes, the distance is only 20. Is that okay? And also the number of edges is not that much. It's not that many. Okay, for each, okay, so let me ask you, how many edges are there? How many edges are there? So there's 1 edge here, there are 4 edges here, there are, how many? There are 12 edges here, right? How many edges here? I hope you still remember the concept of degree, right? The degree of a vertex is the number of edges joining to a vertex. Okay, the degree here is 1. The degree here is 2. The degree here is 3. Why is it 3? Because there are exactly 3 strings that is different from me by exactly 1 bit. Am I correct? Everyone has degree 3 here. So here, everyone should have degree 4. So the number of edges in total here will be 4 times 16. Is that okay? And in a Q5, the number of edges will be 5 times 32. Is that okay? And then in a Qn, the number of edges will be what? It will be n times 2 to the power, no. It's not 4 times 16. Okay, I forget to divide it by 2. This is the handshaking lemma. Okay, I should divide it by 2. So it is n times 2 to the power n divided by 2. Is that okay? So this is the number of edges. Okay. And there is one more special graph. And then I will tell you about this and then ask you to think about this. There's another type of graph called bipartite graph. So bipartite means bi means 2, partite means parts. So a graph is bipartite if we can divide it into 2 groups, divide the vertices into 2 groups such that edges are only joined between vertices in one group to the other group, and there are no edges joining to each other. So this is an example of a bipartite graph. Is it a bipartite graph? Is this one a bipartite graph? Definition again, bipartite graph is we can divide the vertices into two groups such that no edges between the same group. You can imagine what is happening. So if a graph is a bipartite graph, it is possible that we can color the vertices into two colors, let's say black and white, such that all the edges must be from one end with black and the other end with white. There is no white-white connection, there is no black-black connection. So is this a bipartite graph or not? Is it? Yes. Okay. So simply we color this as black and all the others are white, and this is a bipartite graph. Is that okay? And then let me give you. How about this one? Is this a bipartite graph? No, this is not a bipartite graph. And yeah, so why? Because if it is a bipartite graph, then let's say this one is colored in black, then these two has to be in white. Am I correct? And because these two are in white, these two has to be in black. And then we get a contradiction. There is a black-black connection. Okay, now we don't have much time today. So here is my question for you. I suppose that somebody, your friend, gives you a graph, and you want to check if this graph is bipartite. How can you do so very quickly? So is it possible to do this in linear time? So linear means that the running time should be linear to the number of edges and to the number of vertices. Okay, if the graph has 10 edges and 30 vertices, then it should run in order of 30 plus 10. So if a linear time algorithm for a graph problem is if it can run in order v plus e time, this is the number of vertices in the graph, and this is the number of edges in the graph. Okay, so let's talk about this more next week. Okay, thanks a lot. Okay.